The inner edge of the Oort Cloud is roughly 300 years away. Not 300 years at a leisurely cruise, 300 years at the speed of Voyager 1, the fastest escaping object humanity has ever launched. A spacecraft that left Earth the same year the United States declared independence would still be decades short of even grazing its outer boundary. And Voyager 1 is already considered one of our greatest engineering achievements. That single fact should tell you everything about what we're dealing with. But it doesn't even scratch the surface of why no spacecraft, not the ones we have, not the ones we're planning, and likely not the ones our grandchildren will build, can make it through. Most people draw the edge of the solar system somewhere past Neptune, maybe Pluto. The textbook version ends there, tidy and manageable, at roughly 30 to 50 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers, so 50 AU sounds significant. It is significant. But the Oort Cloud begins at somewhere between 2,000 and 5,000 AU, and it stretches outward to an estimated 100,000 AU. That outer boundary sits nearly a quarter of the way to the nearest star. This is not a region of space, it is a cosmic waiting room that dwarfs everything we have ever explored, mapped, or imagined reaching. The gap between Neptune's orbit and the inner Oort Cloud alone is larger than every human space mission ever attempted, combined, multiplied by orders of magnitude. Here's where the dream comes in, and it's worth acknowledging because it's genuinely compelling. The Oort Cloud represents the final frontier of our own solar system. Beyond it lies interstellar space, the true void between stars. Astronomers, engineers, and science fiction writers have long imagined a probe that could traverse this distant shell, cataloguing its ancient comets, mapping the gravitational edges of our sun's dominion, and eventually punching through into the space between stars. Some envision it as a waypoint, a staging ground for interstellar travel. Others simply want to know what's out there, in that dark, cold region where the sun is just another dim star among billions. The curiosity is legitimate, the ambition is admirable. The physics, however, is devastating. Voyager 1 launched in 1977. It is, as of now, the most distant human-made object in existence, sitting somewhere around 160 AU from the sun. Scientists celebrated when it crossed the heliopause, the boundary where the sun's solar wind is overtaken by interstellar medium, at roughly 121 AU. That crossing took 35 years. At that same velocity, reaching the inner edge of the Oort Cloud would take approximately 300 years. Reaching the outer edge would take closer to 30,000 years. To put that second number in perspective, 30,000 years ago, anatomically modern humans were painting cave walls in southern Europe. Agriculture hadn't been invented, writing didn't exist. The concept of a nation-state was 25,000 years in the future, and a Voyager speed probe launched today would still be threading through the outer Oort Cloud, when whatever civilization exists then looks back at us the way we look back at cave painters. The obvious response is speed, build a faster spacecraft, and yes, engineers and physicists have spent decades on this. The Parker Solar Probe, using gravitational assists around the Sun, has reached speeds close to 163 kilometers per second at perihelion, nearly 10 times faster than Voyager. Impressive, transformative even. Apply that speed to an Oort Cloud transit, and the outer boundary still takes roughly 1,800 years. That's faster than before. It is not a solution. Proposed concepts like nuclear pulse propulsion, where a spacecraft rides the shockwaves of sequential nuclear detonations, could theoretically push speeds to a fraction of a percent of the speed of light. Even at 1% of light speed, crossing the full Oort Cloud takes over a century, and nuclear pulse propulsion has never been tested beyond theory, faces international treaty restrictions, and requires a mass of fissile material that no current launch infrastructure could get off the ground. The rocket equation, the brutal mathematical relationship between fuel mass and final velocity, turns every attempt at radical speed into an exercise in diminishing returns. The more fuel you carry to go faster, the more fuel you need to carry that fuel. The problem eats itself. Then there is the environment itself, and this is where the Oort Cloud becomes something almost hostile in its indifference. The temperature in the outer Oort Cloud hovers near 4 to 5 Kelvin, just a handful of degrees above absolute zero, the lowest temperature physically possible. Electronics are not designed to function at those temperatures indefinitely. Lubricants freeze. Materials become brittle in ways that laboratory testing on Earth cannot fully replicate over decades of exposure. Power is another catastrophic constraint. The Voyager probes run on radioisotope thermoelectric generators, slowly converting the heat from decaying plutonium into electricity. By the time either probe approaches the inner Oort cloud, centuries from now if they survive, their power output will have declined to essentially nothing. Solar panels are useless at those distances. The Sun, at 100,000 AU, delivers roughly 100 billion times less energy per square meter than it does at Earth. A solar panel the size of a football stadium would generate less power than a small flashlight battery. And the debris. The Oort cloud is populated with billions of cometary nuclei, ancient primordial objects left over from the formation of the solar system. They are not neatly arranged. They exist in a spherical shell of unpredictable orbits, disturbed periodically by passing stars and the gravitational tide of the Milky Way itself. A spacecraft threading through this region faces collision risks from objects we cannot map in advance because we cannot see them. Not because our telescopes are insufficient, though they are, but because the objects are dark, cold, and separated by distances that make pre-navigation essentially impossible. A probe moving through the Oort cloud is moving blind through a field of debris for centuries with no ability to communicate meaningfully with Earth. At 50,000 AU, a radio signal traveling at the speed of light takes nearly 29 days to arrive. Mission control cannot respond to a crisis. There is no mission control. The spacecraft is entirely on its own, and it has been on its own for longer than most human civilizations have existed. The onboard systems compound every other failure. Cosmic radiation at those distances, liberated from the partial shielding effect of the Sun's magnetic field, degrades electronics steadily, flipping bits in computer memory, corrupting navigation data, introducing errors that accumulate over decades into total system failure. Mechanical components wear, seals degrade. The entire engineering premise of a spacecraft assumes a mission duration measured in years, perhaps a decade or two at the outer edge of ambition. No spacecraft has ever been designed to operate for 300 years, let alone 3,000. The materials science alone is an unsolved problem. The failure modes are not edge cases, they are certainties. It is not a question of whether systems will fail on a multi-century transit. It is a question of which systems fail first and how quickly the rest follow. Put it all together, and the picture is not one of a difficult challenge waiting for better engineering. It is a picture of compounding impossibility. The distance requires speeds our propulsion systems cannot reach. The speeds we might theoretically reach still require centuries of transit time. The power requirements at those distances exceed anything we can generate without a fuel source that would require decades to decay into usefulness. The environment destroys electronics, freezes mechanisms, and blinds navigation. Communication is functionally impossible, and the debris field makes survival probabilistic at best. Each of these problems is, on its own, potentially solvable given enough time and technology. Together, across a journey measured in centuries through the coldest and darkest region of our solar system, they constitute a barrier that no spacecraft built on known physics and known materials can survive intact. Not with current technology, not with the technology on the horizon, and not, if we are being precise about the physics, with any technology that respects the fundamental constraints of mass, energy, and time. What is remarkable is that we know the Oort cloud exists at all. No spacecraft has ever visited it. No telescope has ever directly imaged one of its objects in situ. We inferred its existence from the paths of long-period comets, ancient chunks of ice and rock that occasionally fall sunward from impossible distances, tracing orbits that could only originate from a vast spherical reservoir far beyond the planets. Jan Oort worked this out in 1950 using nothing but mathematics and the observed trajectories of comets. We mapped the edge of our solar system from our living room, essentially, using geometry and gravity and careful observation. That is a genuinely extraordinary thing. It means that the limits of our physical reach do not define the limits of our understanding. We have touched the Oort cloud with mathematics when no machine could ever reach it in a human lifetime. We may never send a spacecraft through the full extent of the Oort cloud. The honest assessment of the physics suggests we won't, not for a very long time, and perhaps not ever with biology on board. But every long-period comet that swings past the Sun is a messenger from that place, ancient, unaltered since the solar system formed, carrying chemical signatures of a time before Earth existed. We can study them, we can model the cloud's structure, we can understand it from here, across an unbridgeable distance, which is its own kind of miracle.